One was to obtain this limits, a certain class of limits when you take t going to infinity, etc. in the propagator. And then I switched and talked about Jacobi action and how to do the path integral over the Jacobi action. So I want to carry on from Jacobi action and do the relativistic path integral, etc. today. But before I do that, there is one topic related to taking the limits in the Euclidean time, which I want to finish off. I forgot to mention it yesterday, and then I thought I will probably do it later on when we need it, but that will be a disjoint thing at that time. I would like to finish off all the preliminary things which we need at one go before we get into the relativistic domain. Okay. So let me do that first, and then we will continue from the Jacobian. The result which I want to obtain is closely related to this limit which we wrote down. We wrote it down in the Euclidean time, but if you do it in Euclidean time and then switch it back to the real time, roughly speaking, what we said was the limit of this x2, x1, when t is very large, is essentially given by the ground state amplitudes. That is, this can be thought of as phi at x2. The ground state is real, so instead of star I can just write phi at x1 e to the minus I, the ground state energy E naught t. As I said, this is not strictly true, or rather it is not mathematically rigorous to do this entirely in real time, because we don't know how to take the limits. But if you do it in Euclidean time, only the lowest term will contribute, and then you can switch it back. Okay? So we had this. But from this, you can obtain a very interesting result, which we will need in field theory all along when we started off. I mean, this is a particular approach to field theory. This has to do with how a system responds when we perturb this. Okay, and this is a very German concept, and it is used in condensed matter physics quite extensively, and it is also used all the way in field theory, as we will see. The idea is that almost all the properties of the system can be understood by saying, if I perturb it slightly, what is the response of the system? And by using sufficiently clever kind of perturbers or sufficiently German kind of perturbers, the properties of the system can be obtained by its response to this perturbation. So what one has in mind here is something like this. You start with a Lagrangian for the system. I am talking in the quantum mechanical context, and even I will even stick with, when necessary, just one dimension. It is not needed. So if I am talking about 3 dimensions, this is the vector minus v of x. This is your original Lagrangian, which let me call L0. And let us say you want to study its properties. What we are going to do is to change this Lagrangian to L0. We add to the potential a term which is of the form j of t, x of t. So if these are the vectors, I can put a dot product. Okay. So what have I done? Originally my system was time independent, and it had stationary states, E1, E2, E3, which are the stationary energy states. If you want to focus the mind on something, think of it as harmonic oscillator. So you have a nice harmonic oscillator system with states labeled by energies. What I am doing here is to add a time-dependent perturbation to this. This j of t is an external source which is in my hand, and I am just adding this perturbation linearly coupled to x. Okay? And this j is something which I will assume was switched on at a time minus t. So it is j is non-zero only in the intervals of minus t to plus t. So you switch it on at minus t, then switch it off at plus t. Okay? And you originally start the system, let us say in the ground state, and you switch it on at minus t, the external source, switch it off at plus t, and you want the system into the far future. And you ask the question, what is the amplitude that the system which was originally in the ground state before the source perturbed it, continues to remain in the ground state at the later. Now, obviously, this amplitude or the probability associated with this amplitude is going to be less than 1. So, again, think in terms of oscillator, and I switch on a time-dependent perturbation. You have studied this in perturbation theory in quantum mechanics. It will cause transitions to the higher excited state. So, there is a non-zero amplitude for it to go to the higher excited state. So, there is a non-zero amplitude for it to be found at an excited state later on, which means that the amplitude or the probability for it to be found in the ground state is going to be less than. So, this probability contains significant amount of information about the background system if you can compute it for an RBC JFT. Now, that is a big if. For a general kind of a coupling, it is not very easy to compute it, but we will come up with methods of doing that. And that is where the whole game lies. Once you can compute it, it tells you something about the system. Now, it is not necessary that you have to do this way. In a more general context, I could have just taken this and I could have changed any of these parameters to time-dependent parameters. For example, if I am talking about harmonic oscillator, I had a frequency omega square in it. And I can make this omega square of t time dependent. So this omega square of t goes from some omega 1 when t is equal to minus infinity to, let's say, omega 2 at t is equal to plus infinity. This is again a very physical process. You had a harmonic oscillator potential which is a x square potential, and when omega changes it either becomes broader or smaller. So if you start the system at the ground state, it is having an energy half h cross omega 1, and even if you sort of gently change the system at very late times, when I say gently change the system, I am assuming that it doesn't really go to excited state. At all the times it is remaining in the ground state. But even then, at the end you would have found that its energy has become half h cross omega 2. Right? Because it is going from one ground state to another in a very gentle fashion. This much of energy you should have supplied. Okay? And that is important because the external agency, this will back react on the external agency, and this is precisely what happens in many quantum field theory contexts, that you have an external source and that source perturbs the vacuum state, which is like the ground state. And it goes from one vacuum state to another vacuum state, but the ground state energy would have got shifted. A more drastic thing is when you are not doing it so gently. You change omega to a time-dependent function. It started from some omega 1 as the frequency, and as it evolved, there was transition from this ground state to higher excited state. In the particle physics language, this would have been thought of as genuine particle production. So the particles have been produced. What you originally thought was a vacuum state, later on is not a vacuum state. So this need not come because of the linear coupling, even though the linear coupling is a very nice thing and we will keep using it as a probe. But it could have been more complicated. So what we are interested in is what is the ground state to ground state amplitude because of the switching on and switching off of this thing. And I will derive a formula for that in terms of the propagator. And that's what I want to do. Okay. What we will do is to now consider this amplitude when there is a time dependent perturbation, not that yet.
There has to be a justification for it to be perturbation, right? So the T, what is that?
Fine. So when I use the word perturbation, I really made a modification of this original thing. In no sense we are assuming it is small. Okay, so it is not better. Now it's a good question. I mean, the word perturbation is used differently, and in fact, English connotation is that it's a small change. I'm not going to use that. Okay, it could be very drastic. And in fact, it has to be fairly drastic for some of these features which I am talking about to happen. Only condition which I am imposing on it is that it is switched off at minus, switched on at minus t and switched off at plus t. It could be very drastic, it could be strong. I'm not going to say that there is an epsilon here, etc. Okay, and you will find that even with such a strong perturbation, as long as this is done, there is a way of handling things, which is more than your usual perturbation theory where you do an expansion in order by order. Of course, in some practical context, that may be the fastest route to the answer, but right now I am not making that assumption. So if you take this, let us consider after this this has been, you start with this Lagrangian, and somewhere along the line you have added a perturbation by adding a term or making some of these quantities time dependent, and you have made sure that that perturbation is non-zero only in this limit. Okay, we have done that. Then you have another x2, x1 which has been computed. Okay, we don't know what it is yet, but we have it. And I want to look at the following amplitude that we call this p, which is limit t2 goes to infinity, limit t1 goes to minus infinity of this x2, x1 with a particular external perturbation, so I am putting it as J. As I said, it could have been a time dependence of some parameters. So you have this object and I want to compute this. Now we already know that when you do these sort of things, there is some nice asymptotic limit coming up. But here you have a problem because this system with a time dependent J does not have nice energy eigenstate. So everything which I did previously with a nice time dependent eigenstate doesn't work here. However, I can play the following trick. I can write this object as, you start from some x1 at t1 and you go up to some value x at this minus t. Until that time I know everything is fine because there are well-defined stationary states. So what I am going to do is to write this as some integral over dx, and as you can see there will be another integral over dx prime at plus t in terms of several transitions. I am going to look at it at t2. Okay, let me write it as t2 x2 from time t, let us say x, then time t x to time minus t x prime and time minus t x prime to t1 x1. This is standard quantum mechanics. You start from t1, read it like Arabic. t1 x1 to x prime at minus t. This part is completely understood because there is no source at that time. Then from minus t to plus t, I don't know what is happening because there is a source which is acting on it. Then from plus t to t2 also, it is completely understood. So I want to take this and take the limit of this quantity. So I'll have to write this something here. So I'll just put a symbol L. That symbol L is just convenience of writing. It stands for this limit. Okay? That L is an operator which essentially tells you you are taking this. So what happens then? Something very nice happens because in this, when I take t2 going to infinity, there is a e to the minus I t2 minus capital T. That will just pick up the ground state by this rule, right? Similarly here I will pick up only the ground state. So this can be written in the following form. This is going to be like, let us look at this object. So I will have here dx, dx prime. Let us look at this. That is phi at x2, phi at x, e to the minus I e naught. Just make sure I don't make a mistake in the algebra. Minus t, that is for this. Then I have that in between thing, t x minus t x prime, which is what I am after. Then I have this, which is again going to be phi at x prime, phi at x1, e to the minus I e naught minus t minus t1. Here's what we have. Right? So let us group things together. Phi at x2 goes for a right. In this t2 term goes for a right. Phi at x1 goes for a right, and here the t1 term goes for a right. That can be taken outside. What will it give me? It will give me phi at x2 e to the minus e naught t2, then phi at x1 e to the plus e naught t1, which is like minus of minus t1. So that is exactly this quantity. Okay. So that can be written as x2 x1 with, of course, these limits are always understood. In the presence of j is equal to 0, then it is multiplied by the remaining factor, because that doesn't depend on x or x prime. That is why I could pull that out. Then you have an integral over dx, integral over dx prime of the remaining quantities, which I am going to write as phi at x e to the minus I e naught t star. This is real, but here I have a plus I e naught t, but I write it as minus I e naught t and put a star, so that is taken care of. Then I have this in between thing, tx minus t x prime. Then I have exactly the same quantity here without this star. Phi at x prime e to the minus I e naught at minus t. That is going to be e to the plus I e naught t, which is exactly this. I mean, just see that everything works out nicely. Okay. Now we are out of woods. This is fine. What is this object? Here. This is the wave function at time minus t, because you start from a ground state and you have propagated it to e to the minus I e naught t. Okay, this is the wave function at minus t. This is the wave function, the ground state wave function at plus t. This is the amplitude for it to go from here to here. So this is exactly what we call the ground state to ground state amplitude. This is the amplitude for the system to be in the ground state at plus t if it started out at the ground state at minus t. This is what we are after. Therefore, we have the result that the ground state to ground state amplitude, which well, let me call it G, okay, is given by the ratio between this quantity and the quantity on the left. Of course, this quantity is also taken with the limit of t2 going to plus infinity, t1 going to minus. I didn't write it explicitly. So that is given by limit t2 goes to infinity, limit t1 goes to minus infinity of x2 x1 j upon x2 x1 j is equal to 0. This is a very nice result. What it tells you is that if you know the propagated kernel in the presence of an external potential or external time dependent perturbation always understood that modification, and you divide it by the same amplitude in the absence of this source. Okay, so what has changed in the propagation amplitude because of the presence of the source? That ratio, when you take the limits of very long time, tells you the amplitude for the system to be to remain in the ground state if it started from the ground state. In quantum field theory, it is called the vacuum to vacuum amplitude. The ground state will be identified with the vacuum. So if you start the system in the vacuum and you end up and you find that the system has to be in the vacuum in the late state, there is an amplitude and an associated probability with it, and that quantity is expressible as this ratio. Now the question is this quantity pure phase? I mean, is this quantity 1? If that quantity is 1, then nothing is happening. Your perturbation is not doing anything, it is remaining in the ground state. That is very unlikely to happen. The second thing which can happen is that this could be a pure phase. It could be e to the I times some quantity. If that is the case, what it indicates to you is that the probability associated with this is still 0. The probability for excitation is still 0. The probability associated with the vacuum is unity. It has not got excited. But what will that phase tell you? That phase will tell you how much of energy changes happen, because the phase will be some e to the minus some I, some quantity into T2 minus T1 when I take this. We will see examples of that. So you can ask how much of this energy shift has occurred under a gentle perturbation where excitation hasn't taken place. So now if the mode square is actually a number which is less than 1, then it is going to tell you what is the probability that it has been active and excited. So then the probability in the field theory context, the vacuum state is not a vacuum state any longer in the end, which means particles has been produced by the external perturbation. So the probability that particles has been produced is 1 minus this probability. Okay, so the probability for a particle production can be immediately assigned. So this is yet another limit which can be worked out because of that Euclidean continuation, because all these, behind the blackboard is the support coming from the fact that this limit can be written down to the Euclidean case and translated, even though I worked everything out in the there. Okay, fine. So this is just one topic which I wanted to finish off here itself before going further. Now we will proceed further with the Jacobi action, properties of that propagator from the Jacobi action, and how it ties in, how it can be used to calculate the relativity problem. Okay, so let us recall what we proved in the last lecture. What we said was, you can have one more probability. I run out of symbols, so I'll call B that also, which denotes the probability that a particle with energy E will go from x1 to x2. So our normal propagators tells you x1 t1 to x2 t2. Now we want it in energy space, so we are asking for the amplitude for a particle to go from x1 to x2 if its energy is E. Okay? This we said can be computed in two different ways. One way is you sum over paths with just the boundary condition x1 and x2. This is the sum over the paths of the Jacobi action, which is exponential I integral square root of 2m into t minus b dm, where L is the integration along the path and the path goes from x1 to x2. Okay? So this was the amplitude obtained by summing over this is the Jacobi action, this is summing over the Jacobi action, and it gives you the amplitude for it to go from x1 to x2 with an energy. You should check with your notes, and if there is some side move or something, you should point it out, but I think it's correct. But then we said that this can also be expressed as integral 0 to infinity dE with some constant c, just to take care of dimensions, etc. E to the IET of the standard path integral. Okay, I could have written it as just x2 x1, which is the notation we have been using. Or more explicitly, this is c integral 0 to infinity dE e to the IET times this x2, x1 is another particle, which is the summation over x of t exponential I, the standard action. And this is our usual sum over parts action. Okay. So this is the result which we obtained. Now first I want to study. So we already know that if we know how to compute this, we can compute the square root. Okay, this is the square root of dl square. So this is what we are going to use, and we will get an expression. But then that expression happens to be a Bessel function. Okay, so I don't expect any of you to stare at a Bessel function and figure out all its properties. So it's a good idea to spend some time and understand what this kind of P will be and what kind of interpretation you can give to it, what are its properties, etc. in a familiar setting. So I want to stress a few properties of this which is rather surprising. First one I had already mentioned yesterday. This can handle tunneling. Okay? If you say that, in fact I had some discussion with Gaurav later on. So since others could also have the same doubt, let me clarify that. If you take a potential, a finite potential, finite height dies down at infinity, nice potential, a potential bomb, and you say that I want an amplitude for a particle to go from x1 t1 to x2 t2 in the presence of this potential, you can always find a classical path which will connect this. Because the path will just adjust itself that its energy is above this. Okay, so there is no problem. But if you say that I want the amplitude for the particle to go from x1 to x2 with an energy E, that is, if you try to do the same thing with Jacobi action, then you will find Jacobi action becomes imaginary if you choose your E and G in such a way that this quantity is negative. So there is already a drastic difference in these two cases, which will hit us at various places in various forms. This is the first thing. Second thing is this property of transitivity. See, we made a lot of sum and dance about this x2, x1, and we will continue to do that. Is transitive. That is, if you go from x1 to x2 and then x2 to x3 and integrate over the spatial coordinates in x2, you end up getting the propagator between these two. Right? Now we can ask whether this is true here. Okay? Suppose I want to go from one point to another and then extra. Will it happen? Now it turns out this is not transitive. That is, the amplitude for a particle to go from x1 to x2 with an energy E and x2 to x3 with the same energy E integrated over all intermediate x2 is not the probability amplitude for it to go from x1 to x2. Okay. I mean, nobody said it should be, but it is interesting that it is not, and I wanted to derive that. So the easiest way to do that and various other things is to give a different representation for this probability, which I will do first. So let us look at this quantity. The probability amplitude E x2 x1. I will use this expression, and just for convenience I will ignore the C. We will reintroduce it in the end if needed. Okay, so what we have here is integral 0 to infinity dE e to the I t e. What is this? This we have a different form which I want to use. This is nothing but x2 e to the minus I t h x1. Right? In the standard Schrodinger picture. I also want to ensure at this stage that the integrals converge, which will turn out to be important later on. Right now we are not calculating anything, so it is not an issue. So when t goes to infinity, everything should be fine. That is easily taken care of by taking this e to e minus I epsilon. Yesterday someone asked, where do we put I epsilon? By and large, you put it by checking what is the right place for it to go. So this is, okay, is this correct? No. I should put plus. Okay. So that takes care of, no, we are making a mistake. This is an integration over t, not over e. T, of course, the result happens to be the same. So, did I make a mistake here also? Yes, nobody pointed it out. Okay, this is an integration over t. This is an integration of t. See, this object depends on t and x2, x1. Then you multiply by e to the iet and integrate over t, and you get a result which depends on e. The left hand side depends on e. Okay? So it is e to the it, e is what you have, and you change e to e plus I epsilon. If you do that, then you are going to get this I into I will be minus, epsilon is always positive, and then the convergence at last t is ensured. Okay? Fine. So this is what we have, and this can be written in a slightly different way. You look at this entire object, so you have a t integration over these two. So you have integral 0 to infinity dt x2 e to the let us say I t into e plus I epsilon minus h x1. So this integral can be done. This is just 1 over. So it is equal to x2. Integral over this is 1 by I e plus I epsilon minus h to the power minus 1 x1. But this integral has to be evaluated between the limit 0 and infinity. At infinity it is 0. It contributes only at the lower limit. Therefore there is a minus 1. Minus 1 upon I gives you an I. Okay? So this is what we have. Okay? I mean, if there are algebraic errors, we will have to correct it later on. Just keep an eye on that. So this is the expression for this amplitude written in terms of your standard quantum mechanical notation. Of course, there is some complicated operator here. It is 1 upon some Hamiltonian plus a constant, which should be expanded in a Taylor series to give meaning. But that is the same as this operator. Here it was an exponential of a Hamiltonian. Here it is 1 by the Hamiltonian. I mean, if you know how to do this and you never batted an eyelid on this, it is the same thing here. Okay? Fine. Now this expression is useful in different contexts. So first of all, it will allow you to write down simple expressions, for example, for a free particle, etc. Second, it will allow you to handle things like transitivity in a very simple way. So let us take care of the transitivity part first. So suppose I want to do integral over some intermediate point, let us call it x2, or maybe x is good enough. I would say x prime of probability for the energy E for it to go to x2 from x prime times the amplitude for it to go from your original point x1 to x prime. This is x prime and this is x1. Okay? Now, what we might have expected is that this will be the probability between x2 and x1 once I integrate over x prime. Okay? But that is not the case, and that you can see. What is this object? This object is integral over dx prime of, for both of these, let us use this representation. It is x2 I e plus I epsilon minus h to the minus 1 x prime. Then same thing, another x prime I e plus I epsilon minus x to the minus 1 x1. Oh, this is fine because this is very nice because dx prime integration over this graph and ket combination here can just be wiped out. So it just tells you this. Okay. So now what you get is that I and I will give you an I square which is minus 1, and let me actually keep it as I. Then you get x2 e plus I epsilon minus x to the minus 2 x1. Which of course is not the amplitude for it to go from x1 to x2 because that should have only one factor of this, it has two factors. So now you can see why. I mean, algebraically the reason this happens is extremely trivial. If you had an exponential, see, instead of this, if I had an exponential, then I will have e to the minus ix, t2 minus t1 and t prime minus t1, and you add it up, one of them will go away, and e to the a into e to the b will give you e to the a plus b. So it will nicely go and in between thing will cancel. But instead of exponential, if you have a reciprocal, then that doesn't happen. But you can play a little bit of a trick. You can write this object as a derivative of this object with respect to e, because it is 1 by something. So if I differentiate it with respect to e, I will get minus this square. So now I use this I square being minus, and I use this whole thing to write it as d by de of this quantity with just one factor here, right? With respect to e. Therefore, this is d by de of the probability for e x2 x1. So one nice way of writing this is to say that this entire expression here is probability for e x2 x1, which is what we would have sort of expected. Okay, so this is, well, okay, there is an I factor missing. So this quantity, the derivative of this quantity would have an I, so I should have divided by an I, right? If I have put an I here and then differentiated, that is fine. So since I differentiated only this quantity, this I was hanging on. So what I have got here is the derivative divided by I. So I should have put an I on top. Let us make sure this is correct. Because this quantity has an I, that I into I will give me a minus sign. When I differentiate, I will pick up an extra minus sign. No, that is not correct. Huh? Yeah, which is 1 by I. So I should put 1 by I here. Right? So this is what we have. So this can be thought of as this into 1 by I. Well, you just make sure later on that the I factors are right. It is either on numerator or in the denominator. No. Okay. So what it tells you is that this integral is what you would have liked it to be multiplied by an extra factor, which is the logarithm of that quantity's derivative with respect to it. Essentially, it is not transitive. And that extra factor comes because of this mathematical reason. Now, why am I spending time on this? Because when we finally do the relativistic propagator for a free particle, that is going to be like a Jacobi action, and therefore that will not be transitive. So this basic rule that x1 to x2 propagator for a particle has to be transitive will be completely shattered in relativity. And at that time, I don't want you people to have a culture shock. So I am just showing you that whenever you do it with the Jacobi action, transitivity will go for a toss. Okay. Now let us do one more thing here. This is fine. there is one more consequence of the same thing. Well, more like a result rather than a consequence. If you do this, either one of these expressions, you can write down what it is for a free particle, and that has an interesting form. So let us do this for a free particle. So what we are going to do is you take P of E x2 x1 and let us look at this expression. So I write it as, I will introduce a complete set of momentum states here as usual. So if I do that, I get integral over ddp upon 2 pi over d x2 this object. Let me keep the I outside. You have a E plus I epsilon minus the Hamiltonian is just a function of momentum for the particle. The whole thing to the minus 1 x1, which now is going to be sandwiched with a complete set of states. Okay, this is fine. I have just taken this expression and I have introduced a complete set of momentum states here. So those momentum states will go here and it is sitting here, and I have integrated over all of them. Everything else is the same, right? So we need again these. Okay, let us work this out. So when you do this is nice because this is some operator acting on P, but this thing depends only on P, so I can just replace it by the eigenvalue. So I get I integral ddp upon 2 pi to the power d 1 over E plus I epsilon minus P square by 2m. Because the eigenvalue of the Hamiltonian for a free particle times your usual thing, which is x2 p x1, right? These are just exponentials, and that will just give you x2 minus x1 times e to the I. This we have done before. So this is e to the I p dot x. In this particular case, it doesn't even matter whether you put plus or minus there because it's only p square. Okay. So what does it tell you? So the entire expression for this has an elementary form in terms of a e to the I p dot x times a p square into denominator, essentially. Okay. So why am I not doing it? Because you should try out. You'll again find that for an arbitrary d, it is a Bessel function. Okay. So if you, see, I am essentially computing here the time Fourier transform of a free particle action. The free particle propagated here is going to have a 1 upon t to the power d by 2 coming from the normalization and an exponential I some x square by t. Right? Exponential I x square by t is dimension independent, but you will have a 1 upon t to the power d by 2, and then you will have a e to the I et. I will give it as an exercise for you guys to work it out. So for a general d, it is a Bessel function, but for specific cases like one dimension etc., you can work it out. This is going to orient you towards thinking in terms of momentum space. In real space, as I said, things are all going to be Bessel functions and stuff like that. But if you look at this object in momentum space, that is not only I Fourier transformed in E. Suppose I have Fourier transformed on x2 minus x1 as well, with the separation x2 minus x1. then this will just go away and the answer is very simple. So the Fourier transform of the propagator, once you do a double Fourier transform, both in time and space, the final expression is just 1 upon energy minus p square by 2. Okay? So you can already see one more thing. For a free particle, you would have expected energy to be p square by 2. So the propagator has a pole. The technical parlance is on mission. That is, when the particle is behaving as though it should behave in a classical system, if the energy is equal to energy and momentum are related by energy is equal to p square by 2m, at that point the propagator will have a pole. What will happen when we do the whole thing in relativity is that it's going to be exactly the same expression, but you will have a 2m E, and it will turn out that E you want to use in Jacobi action is m by 2, so you will end up getting a p square minus m square, okay, where p will be 4-dimensional p, and p square is equal to m square is the standard relation for a relativistic curve. Okay. So again, when it comes in relativity, it looks a bit strange, but what I wanted to show you is that this happens even in quantum mechanics, that you will get what is known as an energy denominator. There is also one more point here. This may or may not have been done in quantum mechanics class, so I am going to just make a comment and leave it at that, and you can look it up later on. When you do perturbation theory, what usually you are interested in is the amplitude or the probability for a transition to take place, like when you are doing radiative transitions or radiation hitting an atom, etc. But you also can ask how the state changes, right? So that formula is also written, that what the wave function is to various orders in perturbation. If you look at it, you will find that all of them has the same kind of energy denominator and integrated over the energy. What it tells you is that when you have a perturbation acting on a system, the system in some sense probes arbitrarily high energies. This happens even in normal quantum mechanics. It probes arbitrarily high energies with an amplitude which decays linearly with that energy. That is what it is showing. Okay? And you will find that the same thing happens when you study field theory. Now, probably the real surprise, once you have this kind of a thing, you can also ask the question, what is the probability that the particle started from a point x1 and ended up at the point x1 with an energy? Okay, I mean, it did nothing. It was at a point x1 and it continued to stay at point x1, or so to speak, it went from x1 to x1 in a closed loop in space with an energy. What is the amplitude for that? Believe it or not, that amplitude in quantum mechanics is infinity. Okay, there is nothing to do with field theory. It is infinite in quantum mechanics, as you can see by putting x is equal to 0. So this is the amplitude for the particle to go from x1 to x2. This x is x2 minus x1. So if x1 is equal to x2, x goes to 0. It's a ddp integral up divided by p square. Now, if you do it in one dimension, fine, it will get you convergence. In two dimension, okay, it is p dp upon p square. This is logarithmic at log system. 3 dimension, it is p square dp upon pp, it linearly diverges. Okay. 3 dimension is where we normally live in unless you are a string theorist. So if you do this integral, it is going to diverge in quantum mechanics. Okay. So in fact, this has a connection with a completely different problem in random walk theory, where you ask what is the probability amplitude for a random walking particle to come back to where it started. Okay, and people usually say that the way whether a drunkard will come back to his home and whether a bird will come back to its nest are different, depending on whether you are talking about it in 2 dimension or in 3 dimension. Because the bird can go in 3 dimensions, the drunkard hopefully stays on a plane. Okay, so the integral which you will deal with is almost identical, which we will see when we do a lattice calculation. So I wanted to introduce you to the first infinity of the course, which happens in quantum mechanics when you ask what is the amplitude for a particle to go from x1 to x1 with an energy E. The answer is infinity. There is no simple explanation for that. So we just live with it and we say that we will handle it as and when it comes up. Okay. So that is all I wanted to do as far as the properties of this quantity is concerned. And now we will.
Sir?
Yeah.
So where have you used the thing for the I epsilon? Where are
We have it. This is for the future. Okay. Well, actually we have. Let me just mention that. See, we had this integral, right? Okay, it's probably a good time to do that also. Okay. I didn't calculate it. I said I will give it as an assignment for you to calculate. Okay. If you want to do that calculation, you have to do an integration over p. See, you take care of the angular integration. Finally, you will have a p square or p to the power t. Let us say 3 dimensions. There will be a p square dp with a p square sitting here. Suppose this I epsilon was not there. Then along the real line, it has a pole. Correct? So the pole is at p square is equal to 2me, or p is equal to root 2me for positive e. So along the real axis, you are going to hit a pole, so the integral is not well defined. Integral simply doesn't exist. Okay. That is why we put an I epsilon. Because of the I epsilon, the pole gets shifted, and depending on whether x is positive or x is negative, not x is positive or negative, you close the contour appropriately, and you will pick it up. So even in this expression, I think I epsilon is relevant. It's really relevant only when you want to get the function out of it by doing the explicit integration. But the integral will not be well defined without this I epsilon. So this innocuously introduced I epsilon plays an important role in the momentum representation. Good point.
they're not even saying that it's small. They're not.
No. I epsilon is just a trick. Okay, let me spend a little bit of time on that. See, we put this just to make sure that when you are doing computation, you keep this epsilon as a small infinitesimal parameter. The moment it is a small infinitesimal parameter, however small, the integral converges. Once you have done the integration, you put epsilon to 0. So the epsilon is relevant only in those expressions where if you put epsilon equal to 0, the expression blows up. Like in the integral. So in the integral, it guides you which way to do the contour. Whether it should be shifted, the pole is shifted upwards or downwards. Okay. Fine. It is small in the sense that at the end of the calculation, I am always going to put it equal to 0. Yeah, so now let us go back to this original line which I wrote here, which is this, and we will try to use it to, this is the, now we have finally come to the real part of the course. We want to calculate the path integral for a relative path. So what do we want to do? We want to calculate the sum over paths for a relativistic particle whose action is exponential. It will be minus I m integral over dt square root of 1 minus v square. So let us make sure we understand this. So you have a relativistic particle of mass m. Its Lagrangian is minus m root of 1 minus v square. I am assuming everybody in the class knows this. This is special relativity. Okay? So if not, you should go and look it up. That is, you need to understand that the Lagrangian for a relativistic particle can be taken to be minus m square root of 1 minus v square, and everything will be fine. The best place to read it up is Landau-Lipschitz classical theory of fields, first chapter. So you start with this Lagrangian, then you can, for example, compute its canonical momentum, and you will find it is mv over root 1 minus v square. Then you can compute its energy and relate energy to momentum. You will find E square is equal to b square plus m square. All the standard results will follow. Okay. So this is the Lagrangian on wants to work. So this Lagrangian is integrated over dt, gives you the action, and you put an m here. Again, a note on dimensions. C is 1. So this should have been b square by c square. Lagrangians, like Hamiltonian, should have dimensions of energy. So this m should have been mc square. Okay. Now In this expression, another way of thinking about this is that this is dimensionless. So it has a dimension mass times t. T is same dimension as length because we are talking about Ct. So from the mass I have to extract something with the dimensions of inversely. Remember that the actions are divided by h cross. So what it is standing for is h cross upon mc in the denominator. So what you are doing here is this has some length dimension. It is being divided by the constant wavelength of the particle. Okay, so it's a dimensionless object. But we will work with it. So the first thing we want to do is to rewrite this in a more sensible way. So take the dt inside, then it will become dt square minus dx square. Just taken dt inside and velocity square is dx square upon dt square gets cancelled, and then of course there is the square root. Okay. Now the written in this form, it is very clear that I can use any parameter I like. In particular, I could have written this as this by some d lambda square, this by d lambda square, and a d lambda. Because the d lambda actually cancels, so this is just a nice way of writing it. Therefore, I can use the notation here, which is t dot square minus x dot square. Okay, where dots denote derivative with respect to lambda. And the way we will write that is to just say that this entire expression, this square root times this. So let me do one more step and write it as g alpha beta x alpha dot x beta dot d lambda, which reduces it to the form we want. This is just then summation over the path exponential minus Im integral square root of dl square, or rather just dl. So let me pause for one moment. What is this quantity? If I take this d lambda inside now, okay, just to get this notation right, I am just going to have dx alpha dx beta. Okay, just spend a moment and make sure you understand that. So what was written as root of 1 minus v square is nothing but g alpha beta dx alpha dx beta square root. If you put a d lambda in the denominator and put a d lambda, it will turn out to be fine. If you choose lambda to be nothing but time, then when you do that, you will get v square and a 1. Because that is how I got it in the reverse direction. But g alpha beta dx alpha dx beta, now we are working in 4 dimension. So I would like to be consistent in my notation and write this as AB, AB. So for me, English letters A, B, C, D, etc. go 0, 1, 2, 3. And the Greek letters alpha, beta go 1, 2, 3. And my zeroth component always comes with the positive sign, and the A, B, C, D, etc. comes with negative sign. So I am using a signature which is plus, minus, minus, minus. Okay? So if you take this expression and you take the square root of that, that is what I would have thought of as dl square. So this is nothing but integral over dl, which of course can be integrated. So this is just L. This is very nice. I mean, it is worth spending a little moment on that. You see, the action in non-relativistic physics is a strange creature. It is T minus V. Nowhere else in the physics we come across kinetic energy minus potential energy, except in Lagrange. Okay. Now, why should that play such a fundamental role? Actually, it doesn't. Action is a very nice object. We ruin it by taking non-relativistic limit. The action for a particle to go from one point to another is nothing but the length between those two events. So that length is your action. Okay? M times length. Or length in terms of component wavelength is your action. And that action, when you do all this non-relativistic limit, turns out to be essentially half mv square except for a constant minus mc square. Okay? So in relativity, I mean usually theories which are more exact are more beautiful. And this is one example in point. That in non-relativistic theory, somebody has to postulate T minus V is my Lagrangian and integral of that over dt is your action. And you will say, okay, fine, if it works, it works. But in relativity, there is a very natural way of defining an action by saying that it is just the length of the path. And what it is going to do is to minimize the length of the path. Okay? So that is what we have done. Now, by the same token, we have to get back to this and connect these two. So this is the sum which I want to compute. Okay, I think I have time to write out the sum, so let me do that. So you want to do this, we use this trick. This particular sum is same as this, is what we are going to find. So what will we do? We are going to first put v is equal to 0. That doesn't matter. Then I want this expression to reduce to this expression. So first I find there is an overall minus sign. So it is good to take care of it by taking a complex conjugate. So what I will do is that it is x minus I will put a complex conjugate. And then I am going to take this entire expression and just going to take the complex conjugate of it. So if I do that, this will become minus and this will become a star. So here I will have this minus I and here I will have a minus. Okay? So that is taken care of. So I have to identify this with this. There is a dl sitting there ready to be identified. That is not an issue. I will put v is equal to 0. So that goes away. Then I will choose E is equal to m by 2. If I take E is equal to m by 2, this gives me m. So that length is your action. Okay? M times length. Or length in terms of component wavelength is your action. And that action, when you do all this non-relativistic limit, turns out to be essentially half mv square except for a constant minus mc square. Okay? So in relativity, I mean usually theories which are more exact are more beautiful. And this is one example in point. That in non-relativistic theory, somebody has to postulate T minus V is my Lagrangian and integral of that over dt is your action. And you will say, okay, fine, if it works, it works. But in relativity, there is a very natural way of defining an action by saying that it is just the length of the path. And what it is going to do is to minimize the length of the path. Okay? So that is what we have done. Now, by the same token, we had to get back to this and connect these two. So this is the sum which I want to compute. Okay, I think I have time to write down the sum, so let me do that. So you want to do this, we use this trick. This particular sum is same as this, is what we are going to find. So what will we do? We are going to first put v is equal to 0. That doesn't matter. Then I want this expression to reduce to this expression. So first I find there is an overall minus sign. So it is good to take care of it by taking a complex conjugate. So what I will do is that it is x minus I will put a complex conjugate. And then I am going to take this entire expression and just going to take the complex conjugate of it. So if I do that, this will become minus and this will become a star. So here I will have this minus I and here I will have a minus. Okay? So that is taken care of. So I have to identify this with this. There is a dl sitting there ready to be identified. That is not an issue. I will put v is equal to 0. So that goes away. Then I will choose E is equal to m by 2. If I take E is equal to m by 2, this gives me m. This is what I want. What is it equal to? Let us take this expression and put, of course, okay, I will be also sure about the integration. The integration is going from some limit to some limit. I don't want to use the notation t, that is why I specifically use lambda. So let us take the integration from in lambda from some 0 to tau. Okay. So the integral here has to become integral over 0 to tau. Let me make this expression. Need not confuse the issues. Okay. This is all I need. So 0 to tau. This is tau. And E is m by t. Okay. So I have the result that this path integral which I want to evaluate is given by the standard path integral with some half mv square and all that for a free particle, which is what the Jacobi action corresponded to, times this object with an integration. But this path integral we have evaluated hundreds of times. We know the answer. So let me just write it down. So the final expression is integral c, a constant c, integral 0 to infinity over d tau e to the minus I m by 2 tau times the standard path integral. So let me write down the expression and then I will explain. Hopefully getting it right. M by 2 by I tau to the power half into 4. So I write it as 4 by 2 exponential minus I m by 2 x square by tau. Okay, let us see what this means. Why is this integral, path integral equal to this? It is a free particle path integral, and the action which we are going to have corresponds to the Jacobi action, corresponds to the normal action for this Jacobi action. So that is just the kinetic energy term. We have put the potential energy to 0. And because of that overall minus sign, there is an overall minus sign. And it is m by 2 times x square, because you would have got x2 minus x1 mod square divided by the time. Here of course you will have t2 minus t1 the whole square and modulus of x2 minus x1 the whole square. And the sum over all of them will come with a minus sign. So to be very precise, what does x square mean? X square is a 4-dimensional x square, which is xa, which stands for t square minus modulus of x square. If I had 4 dimensions and all of them were Euclidean, I would have just added them up. Because it is relativistic, there is a in between sign slip. The overall sign takes care that this x square comes with a plus x square. Okay, that is what happens here. And we are divided by tau because that is the time interval over which the propagator is evaluated. What is the prefactor? We know that the prefactor we get is m over 2 pi I times time raised to half for every dimension. So there are 4 dimensions, that would have given you this. But I have put an extra I. That I comes because that is the prefactor you would have got if all the things here has the same sign. So as far as the spatial things are concerned, there is no problem because it is t square minus x square, and when you look at the Lagrangian, it will be t dot square minus x dot square. With an overall minus sign, that will come with a plus x dot square. That is fine. But this is coming with an opposite sign. This is like having one system with a, instead of m, it is minus m. So that opposite sign will flip this sign into one of them, and when you take the square root, that will give you an answer. Okay. So you should sit and make sure that the algebra here is correct. So this is your final answer. What it is telling you, let me write it down here, that a relativistic propagated for a particle to go from x1 to x2 is given by an expression which has the form c integral 0 to infinity d tau e to the minus I m by 2 tau we will keep the I here. M over 2 pi I tau to the power 2 exponential minus I m by 2 x square by tau. Okay. Now I want to do a little bit of massaging of this expression before we stop, because it will take a little 5 minutes more than the usual time. First, I don't like this m by 2 here. I would like to have m. So I just rescale tau by, I will put tau is equal to 2s, let us say. Change the variable, write tau as 2s. So this becomes s. Tau is 2s, so there is an s here and a factor 2 outside. So it is 2ic. Then tau becomes 2s, so this becomes 4. This becomes s. This becomes 4 and this becomes s. Okay, that is just to get this into this form. Then it becomes, I'll write it as 2cm. I'll keep this factor out. I'll keep the I. Then I have taken one m out. There is one m still remaining. So it is m upon 16 pi square. There is also an overall minus sign coming from I. 16 pi square. Integral 0 to infinity ds upon s square e to the minus I m s e to the minus I m by 4 x square s. So that is it. We have actually found the propagator for a free particle in fully relativistic theory, taking into account principles of quantum mechanics and relativity, for it to go from one point x1 to another point x2. Only thing is that it is given as an integral expression over a ds upon s square. You can try to compute this. So this is an exponential of 1s and 1s in the denominator. This happens to be a Bessel function, some k1 of something. So that is why we need to look at it from other angles. I mean, but I told you that the Jacobi action even in non-relativistic quantum mechanics will lead to a Bessel function. So it's not a surprise, and we need to do other things to figure it out. But before we do any of that, I want to give you a simple physical interpretation for that. See, we calculated it using Jacobi action. But what does it mean? What it means is clear the way we attempted the Jacobi action. What is this quantity? If I had given you a hypothetical particle whose action is minus 1/4 m integral xi dot, which is what normal continuity would have been, times d lambda, 0 to tau. Think of a sort of relativistic classical particle whose action is this. Okay. So instead of 3-dimensional velocity square, I have a 4-dimensional square. So this would have been t dot square minus x dot square. Lambda is the one which goes for the dot. Derivative with respect to lambda is what is denoted by this. So suppose I have a Lagrangian like this. Then you can compute what is 0 to x2 at lambda equals tau. We did this long back in the very first lecture. So let me just remind you of that again. What did we say there? We said that in non-relativistic mechanics, you are talking about something like x and t, and you are taking a path which connect 2 points, which all go forward in time. This is 1 and this is 2. At any given time, the paths only cut it at one point. Every path cuts t equals constant slices only at one point, and we are summing over all this. This was non-relativistic quantum mechanics. Then I told you that in relativity, what is going to happen? At that time, I didn't give you proofs. I said that there is going to be a proper time, and here you will have both t and x, space and time, appearing as dependent variables. And you will again go from, well, here of course I have taken lambda equals 0, that is alright. You will have paths like this. This is lambda equals 0, and this is lambda equals tau. And these paths are giving you, they are all going forward in this lambda path. Okay? So this is what happens in relativistic quantum mechanics. So we choose an action like this, and you do this sum over paths. The exact form of the action is not as important as the fact that it is quadratic, and we are doing this sum only forward in lambda. But just as in this particular case, if I had mapped the path in y-x coordinate system, I could have had a path which goes like this. Because nothing prevents you from having a path which goes back and forth in a special coordinate y, which is part of this x, which has x, y is this. In the same spirit, in this particular case, nothing prevents you from thinking of a path. If I project it in t x prime, you can very well have a path which is doing this. Okay, so there can be a path which goes back and forth and comes. Okay, so this is, so in the first lecture or something I told you that this is the main difference between the two. You have paths which are going only forward in time. That would have given you this amplitude. Plus, of course, this 1 by s square and some constants. These two things together is going to come from this action. Right? If you do the path integral on this action, this is exactly what you will get. Well, we have done that. For a free particle, it's just quadratic. So you would have got an m by 4 coming from this m by 4. Then you would have got this action, the classical path would have been x square by s. Remember that x square stands for t square minus mod x square. Okay? And this s is just the time difference which you are computing, which I call tau here. So we might as well do it with this. Right? Then there is this extra factor. This is what Jacobi is giving us. This is the action or the amplitude. Then you are saying that the energy corresponding to proper time is mc square. So as the particle is moving in this proper time, you say that look, as measured by a co-moving die, the energy of the particle in its rest prime has to be always mc square. A very nice thing and very physical thing. So the phase has to be e to the minus ims. This is exactly like e to the minus iet, which we put in the Jacobi action. So you put that, and then you say, I don't care what the proper clock showed. I only want the amplitude for it to go from a point t2 x2, an even t2 x2 to an starting from a t1 x1 reaching t2 x2. Therefore, I integrate out the internal time. So I integrate over these. So this is the amplitude for the particle to go from an even x1 to an even x2 in proper time ds. I integrate that over ds with a measure which is e to the minus ims, and I get back the full amplitude. But when you are doing this, you are doing exactly the same sort of thing as in Jacobi action, because I could have done this and I could have said I am going to integrate out the time coordinate, and I asked what is the amplitude for it to go from x1, y1 to x2, y2. I don't care what the time coordinate is. Okay? It is exactly the same kind of a thing which we are doing here, except that here the physical time is also an independent variable. That is what causes all the problems. Okay? So that is why we need quantum field theory. So immediately you realize that in the normal time coordinate which we have, things can go back and forth. So we need to interpret that. And if you start with the one particle state here, there is just one particle here, at this point in between, it looks as though there are three particles. And then it is again one particle. Much worse, I can now have a process like this. It's a complete closed loop, which is what we were talking about in the Jacobi action anyway. There were no particles here. There were no particles here. If you cut this, the path tells you there are two particles. Right. So this is very interesting. You start with a relativistic particle, you do all kinds of jugglery, and in the end you say that when there is no relativistic particle, let me calculate what is the amplitude. Okay, which is what we are doing. So there was no particle, so to speak, there is no word line which is cutting this. And that is a loop. And you can in principle compute that amplitude. You will find that amplitude is divergent, but that divergent expression will contain something extraordinarily meaningful and beautiful, which we will do in one of these days. But these kinds of paths come about in real time and real space. The integration is only over the proper time. And this corresponds to all sorts of things which goes by the name of vacuum fluctuations, etc., etc. So what I wanted to show you is that none of this is any more mysterious than what we have seen already in the non-relativistic quantum mechanics. Okay? So when you do the math, you get two terms, and these are the two terms which they correspond to, and you end up getting. Now there is a little bit on this reparameterization invariance which I want to do. It will take me about 10 minutes. So if Pune University people do not have anything coming up later on or bothering it, I will do it now. Otherwise I can take it up in the next class. What do you want to do? It's okay? Okay. So let me just mention that part. It is not something which is frightfully relevant to what we are doing, but it is good to know what is going on. So in order to do that, let us stare at it a little bit. See, I have this quantity, which will come from a Lagrangian here, which I wrote down, which was minus 1 by 4 m xi dot xi. Now put this I is somewhere. So this is a Lagrangian which I have here, right? But I can take this also into account because this comes from just an integration over d lambda of a constant. So I could have changed the Lagrangian to something else, which is, let us say, this minus n. Now if I had, instead of this Lagrangian, if I use this Lagrangian and I integrate, the first term gives you this action, second term will give me minus m s. That minus IMS is what is here. Okay? So if I take this Lagrangian, then I could have simply said that I am evaluating the integral for that and just integrating out the internal time. That is another alternate interpretation. I need not have said about the proper time having an energy which is mc square, etc. I would have thrown it into the Lagrangian as a constant. But let us look at this Lagrangian. What does that Lagrangian tell you? That Lagrangian has a corresponding Hamiltonian, which you can easily write down, because if this was the kinetic energy term, first there is an overall minus sign, and in the kinetic energy term instead of m I am using m by 2. So normally I would have got p square by 2m. Since m has become m by 2, that 2 goes away. So I would have got minus p square by 2. Then the other term is like a potential energy, minus v. So in the Hamiltonian it will give me a plus n. So this quantity is minus 1 by m p square minus m square. Remember that all the squares which I am writing down now is 4-dimensional. It takes some amount of time for MSc students to get used to it, but please spend time and understand what the notation is. This p square, for example, stands for pi. P square is pi, which stands for the zero component of the momentum, which is e square minus mod p square, which of course we know is equal to m square. So the Hamiltonian is like p square minus m square. Now what does it mean, and how is it that this Lagrangian has anything to do with the relativity? The way it is written down, it is not clear. But I told you that there is a very significant difference between Jacobi action and the conventional action. The Jacobi action is invariant under reparameterization. If I change d lambda, if I take d lambda and you change it into some function times d lambda, the action did not change. But here if I go on changing it, in the denominator I will pick up 2 factors of d lambda, numerator I pick up only 1, therefore it will change. So what I want to do is to rewrite this in such a way that it becomes reparameterization anyway. There is a trick for that. The trick is you introduce one more variable, which really doesn't have any serious physical principle. Wherever you see d lambda, you replace it by some capital N times d lambda, where n is a function of lambda. Okay? Just do that. What will happen? What will happen to the action? First it will pick up an n here. Then it will have a n squared here. So the kinetic energy term will, so this Lagrangian which I wrote down there now will get again modified. So the Lagrangian now goes to minus 1/4 m by n x dot square, which is xi. Then I get a minus m. Now classically when you vary this Lagrangian, normally you vary your xi, which is your dynamical variable, but I have introduced an extra n. So the rule book tells me that I have to first vary n as well. So we vary n, find its extremum and plug it back. Let us see what we get. So if I vary n in this, so this is n is not a, n is just a, it is not, there is no n dot integration etc. So ordinary differentiation will do. So the variation of the first term will give me, sign will be 1/4 m x dot square upon n square. And the second term will give me minus m equals to 1, just differentiating with respect to n. Okay? So this is the condition. M is irrelevant. This is 1. So you know that n square has to be equal to 1/4 of x dot square. So let us plug it back into this extremum value of n. So then that Lagrangian becomes minus 1/4 of x dot square. The n will be the square root of that, so it is minus m square root of 1/4 of x dot square. So x dot square minus m. N is again half square root of x dot square. That is very nice, especially the half. 2 halves together gives you a 1 and you get minus m square root of x dot square. This is exactly the action we started with. Okay? So you have to say that assimilative magic. You start with an action which had a square root. It was x dot square root is just the length. This was what we have called ml, which is the original action. I could arrive at the same action from another quadratic action by introducing an extra variable n and then demanding that when you are doing any computation, I vary both n and this. So suppose you are doing classical physics, then it's obvious. You vary n, you get the answer, plug it back and vary. Or you can vary both and then plug it back. It will turn out to be the same thing. So it is equivalent to varying this is completely equivalent to varying both n and xi in this. You can also intuitively see why that should be the case. This one is reparameterization invariant. This one is not if n is not there. By putting n back, you have reintroduced the reparameterization invariance. Because now when d lambda goes to some f times d lambda, it is same as n going to n times f. Since n is an arbitrary variable, n times f is also an arbitrary variable. So the system is invariant under that. So if you start with a reparameterization invariant action with this quadratic term, there is another way of doing the path integral with this and arriving at the same result. Okay? So the minus 1 part x square kind of a thing which we have written down here essentially takes care of all these features. And if you now do the whole thing and you put it equal to 0, see we had this condition here. In this condition is supposed to hold the solved back for n. If after varying this you put n is equal to 1, you will get the result that this h has to vanish. Which is same as saying that b square should be equal to m square. Okay? So if you want to do classical theory, you can do all these. And when you want to do quantum theory, it is slightly more tricky because you want to decide what is the measure over integrating over n and things like that. That's why I didn't do it this way. But I just wanted to justify to you in some intuitive way why you get expressions like this and why Lagrangians like this describe the same physics. Okay? Fine. So, rest of the discussion will now be sort of downhill, so to speak. We have got the answer, we want to understand the answer. This is the propagator, and what I would like you to appreciate is that we have got the propagator for a relativistic free particle without ever mentioning the word field. Well, I did mention the word field, but I didn't use the concept of field. You don't need any field. You can do this path integral, get the propagator. This propagator will turn out to be what is known in literature for those who are going to read books called Feynman propagator. Okay? And this is the cornerstone in all of quantum field theory. Any calculations you do for Feynman diagrams, etc., will all use this propagator. And in the conventional way of deriving this is from the field theory. I have done the opposite direction and then we will connect up with the field. Okay. Any questions? Yeah.
So normally you would expect this is concerned with transitivity.
Yes.
So you would expect the amplitude to multiply, right? I mean, so I would have never expected the probabilities to multiply.
No, it is all amplitude. I may call it probability, but it is all amplitudes. The Jacobi calculation, what we did was an amplitude. It's not a probability.
Okay,
So that is not an issue. It is just an amplitude.
And you're saying that the amplitude itself will not multiply.
Amplitudes will not be transitive. You can multiply the amplitude.
That if I want to go from A to B to C, so amplitude to go from A to B times the amplitude to go from B to C is not the same as amplitude.
Integrated over all C in between.
Yeah, amplitude over all the C.
It is not. That is the shocking truth of life. It is true if you do this for a non-relativistic particle in coordinate representation. It is not true in the energy representation because the energy representation already involves an integration over all T. So you have sort of screwed up with the interference pattern, so to speak. Any other comment? Okay, fine.